All right. Hello, everyone. Good morning. Thanks for coming this early. We were already worried that a lot of people would be sleeping now that it's closer to summer. So I was invited by Adam to give a talk, and I thought I had this tutorial ready that it would be good for and a little more educational than just a research talk. And this tutorial is basically 2.5 hours on formal verification and control with conformal prediction. And our motivation here is to obtain practical safety guarantees for autonomous systems. Okay. And I have a couple of objectives here. First of all, I want to give you a brief introduction into the type of research, very high level, that I'm doing that motivated me looking into statistical tools. And then I want to give you a tutorial around 45 minutes on conformal prediction, which is one of these statistical tools that we've been looking at. And then in the reminder of the tutorial, I want to show you how we can use this tool, conformal prediction, for safe control design and for runtime verification, for predictive runtime verification. And well, feel free to interrupt me at any time. We can be interactive here and just design this kind of in a way so that it's useful for everyone. Okay. All right. So here it is. First of all, I'll remove this. So what am I broadly working on? I work on autonomous systems like many others of you, and these, at the end of the day, are control systems that operate autonomously in complex and in open-ended environments. And some of the application that I'm specifically looking at is in autonomous driving and robotics. I mean, I guess many people draw inspiration from there. But more specifically at USC, we're also looking in wildfire prevention and disaster recovery. And you can imagine after the wildfires in January in LA, this has become a really hot topic. And so a lot of people at USC are interested in that, including us. We were actually interested in that already before the fires, but that is luck on our end, luck in the sense of that we're doing research on this already for a while. But there are many others. I mean, Pedro here is working on space exploration, right? We have warehouses, agriculture, smart cities, and many other application areas. And this certainly highlights the importance and the potential impact that these systems may have in the future. And really, over the past years, we have seen huge improvements in the design of these systems, partially because of the advancements in artificial intelligence and in machine learning, as well as availability of data. And I've shown 3 examples here: Boston Dynamics robots, Tesla cars, or drone fleets here at the Kumar Lab at UPenn, where these systems really perform highly challenging tasks with ease. And really, just by looking at these videos, we could say, well, yeah, autonomous systems are a reality, right? But the question that I would like to ask you, and that students in my lab, or we all ask ourselves in my lab, is, do we really have all the theories and tools in hand to build these autonomous systems that are also safe? And I would argue that the answer to this question is no, simply because at the same time, we've seen a lot of videos of failed demonstrations, right? Boston Dynamics robots crashing, Tesla cars colliding, or drone fleets collapsing, basically. When I came to the US, I started looking more into learning-enabled autonomous systems, right? I mean, these autonomous systems, they use in some shape or form learning or data, right? And it turns out that these learning-enabled systems are often fragile. In technical terms, they may not be robust. I have a couple of examples here. Cruise in California here recently had to recall all their self-driving cars due to yet another accident. The car was basically dragging along a pedestrian for quite a while. It was deemed unsafe. And even though you could argue that Waymo is there already, that's a video that I took in Santa Monica, where I live, where these cars are amazing, right? You can sit in there, you can drive from A to B. I would still argue that they're not fully safe and certified. Here, for instance, Waymo just recently added a program for first responder kind of detection. And in fact, 3 weeks ago, I was at a conference and someone told me they were in a Waymo and the Waymo car didn't detect police sirens in the police car, basically. So we're not really there yet. And from another domain here, I have a video where a robot is basically headbutting someone in the crowd. And there are a couple of videos on the internet, right? So these are just some examples. The more important question for us is, well, what are the reasons that we're facing challenges in building these systems? And there are plenty. Some that I think are important, and this was realized already years ago, is that the way that we train our AI is somehow fundamentally flawed as we train and tweak algorithms to lab-like environments and pre-specified scenarios and specifications. And we fail to generalize beyond these lab environments, beyond these pre-specified scenarios, and specifications. And another reason is that the AI that we're using is easy to fool. It's not robust. Again, like I said, in technical terms, this is also an old example where we have an image of a panda, the classifier correctly classifies it as such. But when we put some small noise on top of this image, the resulting image to the human eye really looks the same, but it's suddenly misclassified as a given by the algorithm, right? And I have a more modern example along the same lines that was done by one of my friends, Alex Ruby, who is at CMU right now. He's looking into LLM-controlled robots and to jailbreak them. So you could ask the robot, well, deliver the bomb. The robot wouldn't do it. But then he's designing carefully selected sequences of symbols that he's adding to the prompt, and then that would jailbreak the LLM-controlled robot so it would deliver the bomb. So that's also another example of not being robust. The question then, importantly for me at least, is, well, how can we make these systems more safe? But also, what are the fundamental limitations that we're facing, and what are performance and safety guarantees that we can provide? And at least for the guarantee side of things, I'll provide some partial answers here today. Okay, so we're control engineers, everyone here in the room. That's really refreshing. So we like to look at block diagrams. I have a very abstract one for you here. We have a system, in this case, a car, that operates in an environment these days. These environments are dynamic, they're uncertain, they're potentially open-ended, right? And what we typically do is we use sensors such as camera, LiDAR, radar to get some information about whatever is going on in the environment. And we push this through a stack of perception and prediction algorithms to get state estimates about the state of the system as well as the state of the environment. And these estimates we then use basically for planning and control to compute low-level actuations for the system. And we repeat this, for instance, at 100 hertz, right? And just to give you some examples of what learning components we're looking at, for instance, object detectors, we want to detect which objects are in the environment and we want to assign semantic labels, okay? We may want to use trajectory predictors. We'll see this a couple of times today. For instance, at an intersection, we may want to predict whether pedestrians will be within the next 5 to 10 seconds and use that information. Or more classically, we want to use some learning components for system identification or for low-level control itself, right? So there are many core challenges in these learning-enabled feedback loops where we have learning components potentially in there. Some of those that I focus on are, for instance, on the complex environment and the potentially high-dimensional sensors. And what we really need there are uncertainty-aware and reactive control methods. Another thing are the learning components itself. We want to train them robustly, and more importantly, and we'll see this today, we want to verify them online. So we want to, in a fast way, kind of assess, is the information that we're getting good or bad? And we want to look, or I want to look at learning-enabled multi-agent systems, so networks of learning-enabled systems, so to speak. Also, what we're looking at is system specifications. So how can we formulate requirements for such systems that operate in uncertain worlds? And we kind of come up with dynamic formal languages that can capture this uncertainty. We're also using a lot of high-fidelity simulators and photorealistic simulators and data, and we look at how we can mitigate sim-to-real gaps potentially when we go from simulator to the real world. And what's really important for us is that we can do all of this in real time. So we look into efficient computation of algorithms. And what we need in order to do this, and what will pop up today in this tutorial, as well as we'll be working using a lot of control theory, obviously, a bit of formal methods, and machine learning, and specifically statistics. And obviously, these circles are not isolated. We're really working at the intersection here. And the glue that puts everything together are really robust algorithms, okay? Okay, so now getting a little bit more into the analysis of these learning-enabled systems. So to get this started, the question really is that, you know, this is not a linear system anymore with linear feedback, right? This is it's potentially a non-linear system or a hybrid system that may contain really high-dimensional learning components, okay? By high-dimensional, I mean these potentially feed-forward neural networks may have thousands of neurons, right? It may be really complex. And how do we reason about safety of these learning-enabled systems? And there's some existing work. For instance, satisfiability modular theory solver or mixed integer linear programming techniques, hybrid systems reachability like HJB, which you probably know. However, here these tools, they don't really scale to the task at hand, right? They can't deal with these complex systems that we encounter in reality. What these can do is they obviously can characterize, in theory, input-output behavior of neural networks, like reachable sets, or input-output behavior of neural network controlled systems, so reachable sets of these systems, but only of simple systems, right? It computationally simply doesn't scale. And then people have come up with convex relaxations of these problems, for instance, using linear programming or semi-definite programming or compositional techniques. However, since these are convex relaxations, they're typically overly conservative and also don't apply in practice. Okay, so these are, I think, really interesting tools and techniques. However, I would say that they don't really apply to real-world examples. Ideally, though, we would like to navigate this trade-off between scalability and conservatism, right? And on top of that, we would like to reason about stochasticity that enters this feedback loop. We would like to reason about disturbances that act on the system. We'd like to reason about noise that enters on the sensors, right? And specifically here today also, we want to look at randomness in the environment and how it affects the system. And that's when we started out asking ourselves, can we use statistical tools instead to formally reason about safety? Okay. And I want to show you this picture over here that I did myself. So it's not from some textbook or so, but I kind of thought about this myself, where you can see different methods for control design and verification. And on the x-axis, you can see the verifiability of the tool, meaning the more you go on the x-axis to the right, the stronger your proof of correctness and safety is. And on the y-axis, you have scalability, meaning that the more you go up, the more scalable your method is, and to more complex systems, it kind of applies. And I kind of carved out here this red area for learning-enabled autonomous systems. What we see here is that statistical verification in general is highly scalable and still gives you some form of guarantees. And conformal prediction, which I mentioned before, is one of them because it's simple, it's really easy to understand, it's general, it applies to kind of black box systems, and it's really efficient if you use it the right way. And this using it the right way is something we'll look at in more detail today. What one should keep in mind, though, here is that we will not get safety with probability 1. We will be able to talk about task satisfaction with a probability no less than 1 minus delta. So this is always something important to keep in mind. And if you're, after this tutorial, interested to learn more and to see also a lot of related work, you can have a look at our tutorial that we wrote where we kind of try to give an overview and kind of point to different literature that may be of interest. Okay, so the way I kind of structured this is as follows. We'll see an introduction first, then have a couple of coding examples. You can access the code if you'd like to. Then we'll talk small break, then we'll talk about safe control, small break, and we'll talk about predictive runtime verification. One disclaimer here, we focus on what's called split conformal prediction. There's full conformal prediction as well. It's not super scalable, so that's why most of the people who operate in this kind of learning-enabled or on learned systems, they usually focus on the split CP variant, as it's called. Okay, so conformal prediction in a nutshell. It has become quite popular recently for one reason. It gives you uncertainty quantification under minimal assumptions. Okay, what I mean by minimal assumption is that it's distribution free, meaning if we're in a supervised learning setting where we have inputs U and outputs Z, that are drawn from some distribution calligraphic D, then we don't need to make any assumption on this distribution calligraphic D. It could be Gaussian or it could be any funky distribution really that we may experience in the real world. And at the same time, we don't need to make any assumptions on a predictor that we're using. For instance, if we use a predictor mu that takes an input to predict an output Z hat, then this could be a neural network, but it could also be a support vector machine or something more classical like a Kalman filter, right? So it's kind of black box in that sense. What you, however, need, on the other hand, is you need the availability of an IID, so independent and identically distributed data set, we call this a calibration data set, of input-output pairs that are drawn also from this distribution, right? So we have K of these input-output pairs, and those are what we're using. Specifically, what we're using them for is the following. Our goal is that we fix the failure probability delta, so this is what you choose as a user. And then conformal prediction gives you a prediction region C such that a new data point Z is contained in this region C that may depend on the input with a probability of no less than 1 minus delta. Just to give you an example, assume I've given you these three images along with a classifier, then you see that these are of different difficulty to classify, right? The first one is the easiest, and in this case, the prediction region contains only one label, the correct one. The second image here is already more difficult to classify. The lightning is a little more tricky, right? And there are other elements. So here the prediction region may contain 4 labels, and here the head is kind of chopped off. And in this case, the prediction region may contain 6 labels. So quantifying the difficulty of the task, the uncertainty that the predictor, so to speak, is facing. Now, this is kind of the goal, what we're aiming for, and now we need to talk about the technical machinery. So conformal prediction is based, the vanilla version at least, is based on a really simple quantile lemma. This slide is a little more mathy, so I'll try to walk you through it more slowly. We assume that we're given k+1 IID random variables that we denote by R0 to Rk. Okay. And these are usually referred to in this community as the nonconformity score, but for now you can think of it as a prediction. And our goal then is the following. We want to find a probabilistic upper bound for the test data point R0 in terms of the calibration data R1 to Rk. Okay. And what one can show is that with a probability no less than 1 minus delta, this test data point R0 is bounded by the 1 minus delta quantile over the empirical distribution of R1 to Rk, so of our calibration data, and infinity end. Okay. So the way this looks like is we plot the histogram of our calibration data. So here on the x-axis, you have the nonconformity scores, the values. On the y-axis, the frequency. You plot these, you add infinity, and then you take simply the 1 minus delta portion. Now, well, how do you compute this really? All that you have to do, if you think about it carefully, you compute this number p, which is the ceiling of k+1 times 1 minus delta. And then you take the p smallest nonconformity score. So all that you have to do is you have to sort your calibration data and pick the p smallest value. So the complexity is that of a sorting algorithm, right? It's really efficient, computationally really efficient, and you can run this online quite fast, all right? Now, there's also an implicit data requirement because you pick the p smallest score and you only have k of them. P is not allowed to be larger than k, right? Can you get a more explicit bound from this? Well, yes, you can. Since this k here is an integer, you can basically remove the ceiling. This is rewriting this without the ceiling operator. And then you can simply rewrite this and you get this lower bound for the number of data that you have. So roughly, if you pick delta to be 1%, you need 100 data points to get a valid non-trivial bound. The trivial bound would be infinity, right? So another question here is how tight is this bound? We have 1 minus delta lower bound over here for this probability. And you can show under the assumption that these nonconformity scores have a continuous distribution, that you also get an upper bound of 1 minus delta plus 1 over k+1. So the more calibration data you get, you sandwich this kind of probability in between 1 minus delta. Okay, so this is kind of the result that comes from the literature, and there's basically the kind of the starting point was this nonconformity score, right? And for us engineers, control engineers, I think the important question is how can we design or engineer this nonconformity score, right? I think that's also why this conformal prediction has been applied a lot in robotics over the last 2 years, because you saw it was one slide that was the technical result. And for robotics people, the question then is, well, how do we design this nonconformity score for the application in the end? Yes?
How realistic is the IID assumption?
We'll get back to that.
Because if you look at like, even if you look at something like filtering or these standard estimation algorithms that we use in day-to-day, the errors are usually correlated.
Yeah, we'll get back to that later. Okay, so the question is, how do we design these nonconformity scores, right, from a practitioner's point of view? And I want to give you a couple of simple examples. The simplest one is, for instance, for a one-dimensional regression example, where we could choose the nonconformity score to be simply the error between the ground truth that we have in our calibration data set and the predicted output, right? And then we just take the absolute value of it. And in this case, if we apply conformal prediction, we get this statement, meaning that our test data, the error on our test data, is bounded by this quantile over the nonconformity scores of our calibration data, right? So this is what we get right away. And what we can do now is we can simply rewrite this. So we take the absolute value out of it, and then what we get is a valid prediction region that is centered at the prediction and has a width of 2 times the quantile. Again, this is for a one-dimensional regression example. It's a naive kind of choice. There are smarter ways that also reflect heteroscedasticity in the data, meaning that the bound here could depend more on the input, the quantile could depend on the input. But these are kind of details here at this point. I argue it's simple, general, and efficient with the right choice of the nonconformity score. For instance, we had some examples of an F-16 aircraft where we wanted to predict a couple of steps ahead what the altitude would be and the pitch error basically, and we designed nonconformity scores that captured kind of ellipsoids, hyperrectangles, and convex hulls. Okay, you can see those illustrated here, and in black you can see test data points that are covered by these regions with 95% probability. And by setting up the different nonconformity scores, you can see, well, these are all statistically valid, but maybe the convex hull is giving you the tightest coverage, right? So you could, depending on the application or what you want to do with it, you would choose one of these, right? Maybe you want to use the hyperrectangles if you want to design a linear controller, right? But if you maybe have something more powerful as a controller down the line, you may want to use the convex hull and so on and so forth, right? And another example here is we had a car, or in this case, a robot at an intersection that could go with equal probability left, right, or straight. So there were basically 3 modes with equal probability. And here in green, you see the test data points. And by setting up the right nonconformity score, we were able to, did it just turn off or?
Yeah, I think so.
Okay.
You want to try the other?
Oh, it's the microphone or?
Yeah. Don't know if that's.
Otherwise, can you hear me or
Yeah.
is it still on? I mean,
that's the question.
it's, if not, it's also fine.
Yeah, I agree.
Okay. So yeah, so like I said, I mean, here we have 3 modes, left, right, and straight with equal probability. And by setting up the right nonconformity score, we can kind of detect these 3 modes. We can see that there are 3, so we get information in that regard. And we can fit ellipsoids to the data that covers it with 95% probability here shown in black. And just as a baseline, we use the Euclidean norm without doing any trick, and that will give you this red region, which is just overly conservative. It has high volume and doesn't really tell you anything that you have 3 modes there. So here the story is basically you as a user, you have a lot of freedom to design your nonconformity score for the application at hand. Okay. So this was kind of the intuition I think that you should have and keep in mind. I think that's the important part here. The next slides are a little more going into details because I want to tell you a bit about what type of guarantees you really get. I think that's what a lot of people, even published papers, don't get right. And yeah, I think it's important to be aware of the type of guarantees that you really obtain. What you obtain with this kind of vanilla conformal prediction method are marginal coverage guarantees. So marginal here by this community means that the probability that we talked about so far captures randomness in the draw over test and calibration data. So over randomness in R0 to Rk, okay? And this is in contrast to calibration conditional coverage, which we would ideally like to have. We would like to have guarantees of the form, given a calibration data set, this guarantee here holds, right? Where now the randomness in the probability is only in the draw over the test data, right? This is what we would ideally like to have. Here you have a calibration data set, and then whenever you use that, you get these guarantees, right? However, it turns out that this is impossible to obtain without making quite restrictive assumptions. The good news, though, is that if you assume that these nonconformity scores are again continuous, then this kind of conditional probability that we looked at, so here conditioned on the calibration data and taking the 1 minus delta quantile, is beta distributed. And this beta distribution has a mean of 1 minus delta, exactly what we want, and a variance with 1 over k. Okay, so the more calibration data you have, the more you approximate your calibration conditional guarantees. As you can see here in this figure, for instance, right? Here, kind of the larger k gets, the more you get to your spike that is centered around 1 minus delta. And there's another variant of conformal prediction that I personally refer to as pseudo calibration conditional prediction, because you obtain these calibration conditional coverage guarantees with high confidence. And this is what may be familiar for some of you already who work on statistical learning theory. Is you get these kind of double probability statements where you have an outer probability over the randomness in the draw over your calibration data R1 to Rk that holds with 1 minus beta confidence. You could pick beta again. And where then the inner probability here only captures the randomness in the draw of your test data point, okay? But here we're not picking the 1 minus delta quantile, we're picking the 1 minus delta bar quantile, where delta bar is a tightened quantile, okay? And you can pick these in different ways. The details here are not important. This is in the paper. The important thing is all you have to do is to get these different kind of this pseudo calibration conditional guarantees is you pick a different quantile and you know what numbers you have to put in there, right? Any questions on this so far? Everything clear? So now there was a question already on the non-IID case. We assumed so far that we have IID data. What happens if the data is dependent or not identically distributed? It often happens. For instance, in a Kalman filter, if you look at states at different time steps, right, distribution may change. And it's generally a really difficult problem, and that's really where this conformal prediction community is having a lot of innovation right now. So there are new papers basically every other week. Different variants, for instance, robust conformal prediction, adversarial conformal prediction, adaptive versions, weighted versions, and so on and so forth. So there's a huge bunch of literature on that. We'll see two variants today later on, robust and adaptive one. So you'll learn of some of these. And if you're interested, I have literature pointers also in the survey. Okay, so, but I think for now it's important to keep in mind we need to be in this IID setting. If not, we need to do something smarter. Another thing I want to mention is that conformal prediction is one of many statistical tools, right? So there are others like concentration inequality, Höfting inequality. Maybe some of you, let me maybe ask, who of you is familiar with Höfting inequality or have seen it? 3, 4, basically. So keep in mind there are other tools that may be useful for your problem at hand. DKW inequality, Klopper-Pearson confidence intervals, and so on and so forth. Right? They share some similarities. I don't want to go into details if only 3 of you have heard of Höfting, but there are similarities. That's what I want to say. And another kind of thing one could look at is optimization problems under uncertainty. For instance, scenario optimization. Who of you has heard of that? Yeah, also 4 or 5. So scenario optimization is one tool. By the way, there's an EECI course that I recommend. It's kind of a good course where you have an optimization problem with chance constraints, so with probability constraints, right? This distributionally robust optimization, PAC-based theory that's more in a supervised learning setup, or we have something on conformal predictive programming where you want to design decision variables under uncertainty. But again, this is just to give some context. And if you want to have more comparison, we try to do that also in this survey paper. And I think it's a really rich and exciting field to work on. You'll see later, you can use these statistical tools to give some guarantees about learning components, learning-enabled systems, autonomous systems in general when the complexity really blows up. So I just encourage you to, if you're interested, to study this a little more. All right, so this was this kind of swapped. This was the introduction, and the next thing I wanted to do was to give you some more examples. Oh, we're actually really good in time. All right. Cool. All right. So now the question is, having these theoretical guarantees, we want to use them potentially for an application, right? We want to design a controller, we want to verify a system. And then we want to empirically validate our statistical guarantees, okay? So we want to check if the theory aligns with our experiments and the algorithms that we're doing, right? I think that's if you write a paper, you kind of have to do that as well. And what we want to check, for one, is if the marginal coverage guarantees that we have obtained will hold, okay? And in order to do that, we perform capital N experiments, okay? So here, capital N is the number of total experiments, and we pick one. If we pick one experiment, that's small n, basically, right? So we run these n experiments, and in each experiment, we draw a test data point, and we draw a calibration data set, okay? And what we then do is we sum over these n experiments, and we basically see, so this I over here is the indicator function of an event. Basically, if the event in here is true, we pick 1, and we pick 0 otherwise. And the event in this case is the test data point of the nth experiment smaller than the quantile over the calibration data of the nth experiment, right? So for each experiment, we check, is our conformal prediction guarantee correct or not? It's a 0 or 1 or 0 respectively. We sum over these, and then we divide by n, okay? So this is kind of the ratio of how correct our regions were. And we call this the empirical coverage because, well, it kind of emulates our marginal guarantees. And what we expect is as the number of experiment goes to infinity, our empirical coverage will be 1 minus delta. Okay, so as we select larger n, we will see that we approach our kind of theoretical guarantees that we are aiming for. Okay. Now, the other thing that I talked about is conditional coverage, right? And we saw that we cannot get conditional coverage, but we can approximate it. So here we again run n experiments, and for each of those experiments, we sample additionally capital J test data points, okay? So we run a for loop over all experiments. For all experiments, we draw J kind of test data points, okay? And what we then do is for each experiment, we compute a conditional empirical coverage in the sense that we sum over all these J test data points. And we again take the indicator function of each of these J test data points, and we see if the quantile at the nth experiment kind of is correct or not. And then we sum over these and we divide by J. That's kind of the coverage we get for J test data points. Okay. And then what we do is, oh, sorry, that was too fast. We then plot the histogram of these, and we expect that this approximates this beta distribution that we were talking about. Okay? So this is something important if you want to do experiments. Now, first, a really simple example just to illustrate to you how you could instantiate this. Here we have unknown regions, R1 and R2, that are uniformly distributed in the 2D plane. Okay, so this is just something I picked. For instance, it could mean if you draw one realization, it could be R1 and R2 over here, okay? Now, the important part is we don't know R1 and R2. These are unknown regions, but we have sensors that approximately give us R1 and R2 with some variance, okay? And we call these sensor measurements S1 and S2. They are following a Laplacian distribution. We just picked this because we wanted to have a simple example, and we put some variance on top of it, right? So in this case, for instance, if we make sensor measurements, they could be slightly off over here. Now, what we want to know is how close are our sensor measurements from the unknown regions, okay? So we'd like to know for test data point, how close is the sensor measurement of the Lth region from the position of the Lth region, okay? And we want to do so with 95% confidence. And in order to achieve this, when we use the conformal prediction argument, we need to pick this nonconformity score, okay? And we do so simply by picking the maximum over both regions, the maximum error that we're having over both regions. So we're picking sensor measurement of region L minus position of region L. We evaluate this over our calibration data, and we simply pick the maximum, right? Since you're picking the maximum over here, you can basically see that, well, the maximum is bounded by the quantile if you apply conformal prediction. And since it's the maximum, you can just pull out the for all quantifier over here. I hope this makes sense. Now, we empirically validated this. So we kind of ran a couple of experiments, right? And we, here in this case, we plot the histogram for one of these experiments, and we compute the 1 minus delta quantile. That is basically shown over here. And over these experiments, we then computed this empirical coverage. And we saw that for different values of K, of calibration data, the coverage was basically centered around 95%, exactly what we wanted. All right. We also computed the conditional empirical coverage. This was this number CECN. And we plot the histogram of it. And well, I've shown the plot before already, but what you can see here really is that as you increase the number K, you kind of approximate this. Well, you have a kind of beta distribution, and the larger you choose K, the more you converge towards a spike around 1 minus delta. So now the next question is, can we use these regions to do control design? Okay, so we have obtained information about how close is our sensor measurement to the region. Could we design a motion plan for a robot to result in a trajectory that kind of visits these two regions and ends up in a final area? Okay. And what we specifically want to do is we want to navigate the robot to this final location 5,5. And with high probability, we also want that the robot reaches along the way the regions R1 and R2. So what we want is that the trajectory of our robot, so more formally written down, we want that the trajectory x at time 5 and x at time 15 is close to R1 and R2 with high probability. So we can write it down like this. And the question is, well, how can we achieve this? Okay. Now, we can achieve this in the following well. We first note that what we obtained, just talking about region 1 for now, so just about this part, is that our sensor measurement of region 1 is close to the position of region 1. With 1 minus delta probability is C close. C was this quantile, right? This is what we know, what we computed on the previous slide already. If we now enforce, for instance, in an MPC or using some other constraint control method, that the position at time 5 of the robot is epsilon minus C close to this sensor measurement S1, then we achieve our goal. Why? Well, basically because we can use the triangular inequality. We want here that x5 minus R1 is bounded by epsilon, right? So we can use this. We can first apply triangular inequality. Then we have x5 minus S1 plus S1 minus R1, right? We know that x5 minus S1 is bounded by epsilon minus C, and we know that S1 minus R1 is bounded by C, and then we see that we end up with epsilon. So very high level, what this means, we do constraint tightening, okay? We'll enforce this in an MPC fashion, and well, we want to be epsilon close, but we have some uncertainty, and we tighten this inequality with the uncertainty C. Quite simple at the end of the day. And we can do the same thing for our second region. So, well, what we do at the end of the day is we design a big, in this case, it's an open loop controller. I think we don't even run an MPC. We minimize some cost function where we enforce that we're ending up in the final region. We have robot constraints, input constraints. Here we again enforce the final region, and we enforce this kind of constraint that we just derived. That just depends on the sensor measurement and tightens with the uncertainty that we have obtained with conformal prediction. And well, here are some simulations if you want to take a look. Okay, so let me just pull this up. So this is a Jupyter notebook that I can send the slides around, and the link to the Jupyter notebook is there. And you can basically use this to A, reproduce this example, but also B, to take some of the code for the conformal prediction part out if you just want to do it yourself, right? And I don't want to spend too much time on it because it's rather straightforward. But basically, I want to walk you really briefly through it and show you what the conformal prediction part is. And the important thing is here, it's just a couple of lines because it's just a sorting algorithm, really. So here we generate the locations for the regions. This was just some uniform distribution, right? We generate our sensor output. This was a Laplacian distribution. Then we sample locations, right? We do this a couple of times. Oh yeah, I didn't realize that I kind of. Oh, Fernando is there. Hey, Fernando. Yeah. So yeah, so I might repeat that. So here, the first part, you generate the regions, you generate your sensor measurements, you sample from those because you want to empirically validate something, right? And then in the next box, you kind of you compute your non-conformity scores, you put them all in a list, you sort them. So this is kind of the sort command. You pick P, which is this Pth number, and then you simply return the non-conformity score. And that's basically it. Meaning that if you have your data ready and you have the non-conformity scores, I mean, this is technically conformal prediction, these two lines here. Okay, this vanilla version. It's really simple to do. There's not too much to it in terms of coding. And then here in the reminder, we compute all these empirical coverage and this conditional empirical coverage, and then we plot those. So there's some functionalities if you want to use them as well. And yeah. Yeah, and for the control synthesis, I'm sure you've coded up an open loop controller at some point. So this is done over here, but feel free to check it out as well. All right. So that was the first example. Now I want to show you a second example that's a bit more involved already, and that's more along the lines of verification, actually, instead of model-based control design. So here, what we looked at is a cart pole system, which I'm sure you're familiar with. So we have this system down over here where we can actuate the cart basically, and depending on that, there's a pole mounted on it that will move accordingly. We have the position of the pole, the velocity, the position of the cart, the velocity of the cart, the angle of the pole with respect to the cart, and the angular velocity over here. So it's a four-state system. We sample some initial conditions, as shown over here, where we start the system from. And well, here we said just let's train an RL controller. So that basically a controller that doesn't enjoy any guarantees, right? So we're doing some reinforcement learning. In order to do this, we use the OpenAI gym to simulate the system. And then we train a deep Q network, whatever really. And you can see the system over here. You can see it stabilizes, but after a while, it kind of drifts off. Okay. So we want to verify the system. And to begin with, how would you verify such a controller with classical tools, right? It would be really difficult because you have a deep Q network, you have a feedback system that has, a neural network with the nonlinear activation function. So how do you analyze stability of this, right? And here you can actually, in a really simple way, you can do statistical verification by drawing K trajectories offline with a trained controller, okay? First of all, I guess these are the trajectories that you can observe, as is often the case with an RL controller. There's some shattering in the kind of control input and in states accordingly. But what we want to do here is we want to verify that angular position and the cart position is small for some time. Okay, so we're fixing these kind of tolerances of the angular position of 0.2 and the cart position of 4.5. What we want to verify is that for some time, I think this was 240 time steps or so, the errors, the angular errors and the position errors are bounded by these tolerances, okay? And what we simply did was we defined the non-conformity score so note here that if this is positive, you kind of satisfy your specification, right? You obey by the tolerances. If it's negative, it doesn't. So for the temporal logic people here, you could think of this as the temporal logic robustness, right? And then all we do is we set up the non-conformity score to be the negative of this kind of performance function. We apply conformal prediction, and we obtain these guarantees. right? We write it slightly. See, here's the quantile again, and we find a probabilistic lower bound of this performance function. Okay? Now, meaning that if this minus c, the negative quantile, is positive, we satisfy our specification with 1 minus delta probability. So we empirically validate this, and we see that our quantile is indeed negative, meaning that the negative quantile is positive, and we kind of satisfy our specification. Yeah. So, and then we do the statistical verification here as well. Basically, we see where the conditional guarantees are centered around 95% again. And here, yeah, we also have a conditional kind of quantile, and you see it's basically negative. So we can from here draw the conclusion that with 95% probability, we're safe. And that's the guarantees you get. With that, I think we can take a break of 5 to 10 minutes. And after that, we can go a little more into detail of control design. Maybe we take 7 minutes and 5 before we start again. Thanks. Pedro.
The codes. You could have code someone on the slide with what code.
It's on the slide.
Okay.
I just need to send the slides around.
Okay.
I did that later. What do you want?
I wanted to test it now.
Let me give it to you 1 second.
But it's like a lot of trouble.
No, no, you don't have a Mac, right? So
Now that we can play.
I haven't converted them to PDF yet.
You
So
have the slides. You have the link to the co-op, right?
it's
Yeah. So this
no, it's this one is the Jupyter. Yeah?
Okay. You can send. I mean, we can do something super simple if you want. We can generate a QR code and just put it there.
Shall I send the link to you by email and you?
And I distribute. Yeah,
Yeah,
that's
I
fine.
would say that's maybe.
Good.
I'll send it to Adam and to you then. Pedro, I don't have your email address anymore. What is it?
They don't deserve it.
What is it? Pedro R at KTH?
PADR.
P
Yeah.
P
It's the initials. PADR.
P A.
Alpha, Delta. Just put Pedro, enter. And
No, I have PADR. I have Pedro. Okay. Did you get the gist of it, or was it? Okay.
There's the goal then to get to have K to be almost infinite.
Ideally, yeah. So there's also this the more K you have, the smaller you can select delta. So the more confidence you can get, right? Which kind of makes sense. If you draw infinite data, you've explored your distribution, right? And then you have almost probability 1 guarantees.
But in this split conformal prediction, some of the data is used for training as well.
Yes, that's
So then
kind of like what I presented here hasn't even talked about training, right? It's just you have a non-conformity score that is IID.
Yeah.
So there's no training involved, so to speak, right?
Yeah.
the moment you give the non-conformity score a meaning, so you say it's a prediction error,
Yeah.
then the question is, well, how do I get the predictor that you obtain with a separate data set?
Yeah, okay.
Because if you use the training data set with the calibration data set,
Mhm.
then you have dependency into it. Right? There, and that's what full conformal prediction overcomes, but at the expense of retraining the predictor infinitely many times. That's why kind of full conformal prediction, at least in this space, is not often used. It's not easy to do. For those of those that knew Huffing inequality, what are you working on? Who were those? Were you?
Yeah, so metrics calculation.
Okay, so but not statistical learning or anything. See anyone who's working with Alexandre Trottier? Okay, because they are probably quite familiar with this. Did you get it?
Yeah.
And
Yeah, and I also sent you a QR code that you can put on the definitions.
oh, yeah.
So that's well, yeah. Then if you want, because then people can just like
Yeah.
have their problem.
Pedro, I'm way too much of a boomer, I think.
I can take a picture of you with going tutorials.
Yeah, it won't get better from here. Let me actually do a new slide. I'm 5 years without coding now, Pedro.
Sadness.
Yeah, for those of you, Pedro was so kind to create a QR code if you wanna.
The QR code opens better on website.
Really? No. But that would be me.
Or of the Space Lab.
Yes, for
Maybe
space. Yes, for space.
Yeah, so therefore check these webs.
Or something else that would embarrass me in front of an audience.
Actually.
So I'm giving a talk somewhere at a conference, people open it and I'm like, oh no.
Yeah, the QR code should open the GitHub like you said.
Yeah.
So that as an example.
Yeah, let me know if the code isn't well written, then I can crack the whip on my students. Oh, I should. Yeah. All right. I guess we can slowly move on. Now I think the interesting part starts. We'll look into safe control synthesis in a couple of different ways. In a problem formulation, we'll actually see some work of Lefteris there as well. So if after this, it's in towards the end. If you're interested, there's one expert here already. You can always talk to him. So what I want to do is I want to focus on one line of work that we've been doing on safe control in dynamic environments. So we really want to focus on uncertainty in the environment, in the dynamic environment. So you'll see examples of that. And then we want to focus more broadly on decision making under uncertainty. And this animation is actually created by Lev Terrace. So again, talk to him if you want to know more. Okay, so first 30 minutes I will spend on this problem. We want to compute control inputs so that our ego agent, our system, avoids dynamic agents in the environment with a probability of at least 1 minus delta. Okay, for instance, consider that you want to design the controller of a car to avoid other cars and pedestrians in the environment with a probability of no less than 1 minus delta, right? Now, why is this a challenging problem? Well, to begin with, the agents in the environment are dynamic, stochastic, and have potentially unknown intentions, right? So there's a lot of uncertainty in their behavior already. And what's typically done is one is using some form of predictors, learning-enabled predictors, to predict their behavior into the future. But as we realized before already, these predictors are not always accurate, right? They may be fragile, they may sometimes be wrong. So what we want to do is we want to compute this joint uncertainty and we want to integrate it into control, which is typically difficult, right? Now there's existing work, obviously, in planning and control in dynamic environments. For instance, there's a lot of work using vanilla motion planners such as graph or sampling-based methods, A star or R star. However, these usually ignore the dynamic agents in the environment and the uncertainty that comes with it. There's reactive control methods, navigation functions, dynamic window approaches, specifically in robotics, or CBFs that most of you here know. However, since these are reactive, they don't use any predictions of the environment. And in order to show validity of these control methods, you usually consider rather simple system dynamics. We had this discussion yesterday as well. And there's a whole zoo of literature on predictive, interactive, and non-interactive methods using deep reinforcement learning, Gaussian process-based modeling and control. And here, usually, you don't obtain any safety guarantees unless you make rather simplifying assumptions. Okay? And we want to ask the question, well, how can we quantify uncertainty of learning-enabled predictors and then design safe control laws, all right? Now, we were here motivated to use conformal predictions based on 4 observations. If we look at these 3 kind of scenarios or use cases, then what we observe is that the system dynamics are usually well understood and can be modeled accurately, right? We don't really have a problem in modeling a car or modeling a mobile robot, really. I mean, that's something we have those equations at hand. However, the agents in the environment are usually uncertain and in general hard to model, right? But we're living in a data-rich world, so we have potentially large data sets that describe behavior of dynamic agents, and we have really powerful prediction algorithms, potentially learning-enabled, right? And we want to use all of these together with conformal prediction to design safe and computationally efficient control algorithms. Now, before I go into details, I want to show you a high-level overview so that you have the picture in mind what we're going to do after that in more technical detail. We assume here that we have an offline trajectory data set of our environment. And we will, throughout this presentation, we will assume that we want to control the car at an intersection. So we assume here that we have observed already how pedestrians walk over an intersection, let's say, offline. Now, online, we assume that we have available the state, in this case, the position of the pedestrian at time t, denoted by y of t, and potentially a history of those, okay? And then we're using a trajectory predictor, for instance, a learned one, a recurrent neural network here in this case, or a long short-term memory network, to predict the future behavior of this pedestrian, here denoted by y hat of t plus 1, y hat of t plus 2, and so on. And as noted already before, it's kind of unclear how good these estimates really are. They could be good or they could be pretty bad, and that could have an effect on the controller that we're designing to avoid these. And what we're doing is we're designing conformal prediction arguments to kind of come up with these prediction regions that are statistically valid in the sense that with probability no less than 1 minus delta, the pedestrian will be in these regions, right? Once we have these, it's quite intuitive what we'll do. We'll forward these to our robots, right, where we know the dynamics. And in this case, we design an MPC that achieves that a safety constraint C that acts on the system state or the system trajectory X and the trajectory of the environment, and that this safety constraint is non-negative with high probability. Contributions here are computationally lightweight algorithms with statistical guarantees, And we'll see how we can deal also with temporal logic constraints very briefly. And we'll, for the first time, talk about distribution shifts. We'll get back to your question. Yeah. Okay, so first thing we want to do, and which I will spend a bit of time on, is uncertainty representation of the dynamic environment. So we want to compute kind of statistical abstractions of the behavior of the dynamic agents in the environment. First, we model the behavior of the dynamic agents as a random trajectory. So we assume here that y0, y1, y2, and so on, so the states at different times of the environment are drawn from some trajectory distribution calligraphic D, okay? So technically, this could be any discrete time stochastic system, for instance, an MDP, okay? Important here is to keep in mind, we have a trajectory distribution. Now we consider a trajectory predictor where we have observations at time t. We make predictions up until some mission horizon time capital T. Okay, so we're predicting into a finite, for a finite number of steps into the future. And in this case, we use what's called social LSTM. It's a long short-term memory network that you can train. You don't need to know what this is. It's kind of some form of predictor, basically, that in this case, it's social because these LSTMs that each agent has, they're kind of pooled together to model social interaction. Like I said, it's not really important what this algorithm is. This is something that we downloaded. It's an algorithm from Marco Pavone, actually. There are some competitions. It works really well. We downloaded it. You could use any other predictor if you wanted to. For instance, there are extensions of people that use generative models, right? So something more modern. Or you could use physics-based models as well. So you could go really like funky generative AI, or you could go back to your well-established physical models. You could use a double integrator, really, if you wanted to, right? That's a good model or not, well, it depends on how the distribution of the data is. Now, what we want to do is the following. We want to compute these regions, right? And I want to show you two methods on how you can compute these regions. I want to start with the naive one, and we'll improve on the naive one. But the naive one is the most natural one that you would immediately come up with. The naive one is the following. High level, you're designing multiple non-conformity scores. So you're running several conformal prediction instances in parallel that you join together after that. Okay. The way this technically works is you define a non-conformity score for each time tau that you're predicting into the future. So tau could be 1, 2, 3, 4, and so on, up until the final mission horizon time that you are predicting for. And what you're using is simply the prediction error at time tau. So you're comparing ground truth, so position at time tau, minus prediction at time tau. You're building the error and you're taking the norm of it, okay? You evaluate this over your calibration data, and then you apply conformal prediction, but in a slightly modified way. So instead of taking the 1 minus delta quantile, you're taking the 1 minus delta over capital T minus small t quantile, okay? And you're doing this modification because you want to get multi-step prediction regions. You want that for a test trajectory, the tau step ahead prediction error is bounded by this quantile for all steps that you're predicting into the future, right? So you want to reason over multiple events. So you need to join these conformal prediction arguments by using what's called Boole's inequality. It's commonly used, it's conservative though, and we'll see that. So this is statistically valid. We implemented this in Carla, an autonomous driving simulator where we have pedestrians that start at some random position, go to some random position at random speeds. We trained an LSTM in this case, or we used one. I don't remember if we trained it or just downloaded it. But the important part is here that we plot the histogram for the 2.5 second ahead prediction error, okay? What you can see here is in green, importantly, these quantiles, these size of the prediction regions for different mission horizon times capital T. Here 1, 10, 20, and 30, okay? Like I said, they're all statistically valid, but as you select a larger prediction time horizon, larger mission horizon, these regions get more conservative, okay? Because you're doing exactly this union bounding or using Boole's inequality. We observe the same thing for 4 second aheads as well. So observation years, while statistically valid, the size of the prediction region scales somehow with the mission horizon time capital T. And that's not good, right? We would like to do a little better. So how can we do this? Well, first of all, we again notice that we're kind of doing this modification there. So we're computing a modified quantile because we use several conformal prediction arguments. The question is, can we just define one conformal prediction instance? Okay, and yes, we can. For instance, the simplest thing one could do is, why don't we take the maximum over the prediction errors at all time steps? And why don't we normalize them to have roughly the same range? Okay. So now these alphas over here are the normalization constants. I'll show you on the next slide how you can compute them optimally. But for now, you could assume they're 1, for instance. Okay, so they're 1, and you take the maximum over all the prediction errors. You get straight away the following guarantees. You get again multi-step prediction region where the tau step ahead prediction error is bounded by C, which importantly is now the 1 minus delta quantile over this nonconformity score, and you renormalize by alpha. If alpha is 1, well, nothing changes here, and if alpha is selected in a smart way, it will account for the different sizes of prediction errors at different steps. Okay, I think this is best illustrated to give you a picture on a small case study. Here we have, I think these were mobile robots we're predicting, or pedestrians, I don't remember. But in blue, you can see predictions for 20 steps ahead. Okay, and in red, you can see the prediction regions you obtain with this naive approach. Again, they're statistically valid, but they're super large. Okay. And in green, you see the prediction regions that you get with this max nonconformity score that I've shown here, if you select the alphas in a smart way, as I'll show on the next slide. And the advantage is evident, right? You have really tight regions, meaning that you know very accurately where the pedestrian will be, in this case with 95% probability or confidence. We can also look at the 2D kind of plots at specific time steps. Here, for instance, 1.25 second ahead prediction error. In blue, you see test data points. And you see that these max nonconformity score regions really tightly, so with 95% coverage, cover our data, while these union bounding or the naive approach is just super conservative, right? It captures, I think, 100% here even almost, but it's just too conservative, really, right? For what you were aiming for, at least. So one thing I haven't told you about is how we actually compute these normalization constants. So how can we choose them optimally, right? So that we get these tight regions. And we do this by solving an optimization problem. So we want to find these alphas as a solution of an optimization problem, where we first enforce that our nonconformity score, this max nonconformity score, holds over our data, where we minimize the quantile, the 1 minus delta quantile over this max nonconformity score, and where we enforce some normalization budget, right? So by this, we kind of avoid trivial solutions, for instance, alpha being 0. Okay, so this is what we avoid. So we need to do some trick there. Important thing here is you can solve this optimization problem offline to get the alpha. You don't have to do that online. And if you look at it closely, you can see that this is a mixed integer linear complementarity program. Well, why is that? First of all, max operators you can always rewrite as mixed integer linear constraints. Our temporal logic people here know. The quantile you can rewrite as a linear program, which gives you bi-level optimization problem. So you have an inner linear program, and you can rewrite this with its KKT conditions, which will give you a linear complementarity program. Okay, you can do several things. You can remove the integer constraints, and you can then think about, well, it's obviously more efficient, and what kind of optimality you retain. We've done that, and you can take a look in the paper if you want. Okay, so we have obtained these prediction regions, and we'll continue using these for the problem at hand on the next slide. What I want to do is very briefly, because I think it's useful, is a small excursion. I want to show you that this quantile that we've been talking about all the time is a linear program, and you can use that in various ways. That's why I want to talk a bit about it. So how can we computationally encode the quantile? What you can do is you can find an upper bound of the quantile as the solution of this linear program. Okay, so you can look at it carefully, and you basically see you have an E plus part and an E minus part. And these are the parts that are above the 1 minus delta quantile and below the 1 minus delta quantile. And this is what these constraints here are kind of enforcing. Again, I can't walk through it in a lot of detail, but the intuition here is really you're enforcing that 1 minus delta portion is kind of above, and the delta is below the quantile, and the delta portion is above. And yeah, you're enforcing this with these constraints. Okay. It's a linear program, and it's really useful if you want to optimize over a parametrized nonconformity score, as in the previous slide. In the previous slide, the nonconformity score was parameterized by these normalization constants alpha. Okay, so this is something I think to keep in mind. And then you can reformulate these linear program if you want with KKT conditions. Okay, so that's good to know. Okay, so back to our problem. What we did so far was we computed these blue kind of prediction regions, and now the question is, how can we use them for control design? All right. First thing, the most naive thing, not the smartest, is to do an open loop control design. Okay, so we can write this down as an optimization problem. We want to find the sequence of control inputs that minimize a cost function j, subject to some dynamics constraints, inputs constraints, and state constraints. And importantly here, subject to a robust safety constraint. So what we're doing here is we're taking the worst case over all the states in our prediction regions. Okay, so we're taking the infimum over our kind of constraint function, over all the kind of states in our blue prediction regions. Okay. Now, this is again a bi-level optimization problem, right? Here's an optimization problem, and this is the outer one. So if this safety constraint C is Lipschitz continuous, you can have a reformulation of this, in which you kind of, instead of taking the infimum, you plug in the prediction into C, and you tighten the constraint by the Lipschitz constant of L times the conformal prediction region. Note that, for instance, if you're interested in collision avoidance, you use the Euclidean norm. This Lipschitz constant is simply 1. Okay. If you can then solve this problem, you find a safe controller with a probability no less than 1 minus delta. And to illustrate this, a small toy example, here you have 3 kind of robots or pedestrians and a robot that is supposed to navigate around them. And what you can see here at time 0, you compute these prediction regions, you compute the paths or the control inputs, and you just let them run. I think while this works, the drawbacks are obvious. It's potentially conservative because you're predicting into potentially larger time steps. These regions get larger and larger as you predict more into the future. And it may even lead to an infeasibility of this optimization problem, right? So if you cannot solve this optimization problem because these regions are too large, then, well, you don't get a controller at all, right? So natural strategy is some form of receding horizon controller, like a model predictive controller, what we're doing here. So at each time step, we're taking new measurements of the environment. We're making new predictions of the agents in the environment. We're recomputing the prediction regions, and we're recomputing the solution to this optimization problem. So at each time step, kind of we update this robust safety constraint, and we solve this optimization problem recursively. And what we can also do is we can add a prediction horizon over here that we can play to navigate kind of how far we want to predict into the future. Now, under the assumption, and I'll comment on this in a moment, that the MPC is recursively feasible, we find a safe controller with a probability no less than 1 minus delta. Okay, let me just show you the toy example again. In this case, what happens is the robot will at each time update the prediction regions. So this kind of cones, they kind of shrink over time. And if we find a more direct minimum cost path that goes to the goal. Okay, so this kind of works in this example. Let me briefly talk about the assumption of recursive feasibility. I think MPC or receding horizon control strategies in dynamic environments showing recursive feasibility is in general an open problem. Not sure if you can solve it, right? If you have an environment that is completely unknown, where you have completely unexpected behaviors, right? It's kind of difficult to give any recursive feasibility guarantees. Now, what we looked into here is in a paper that I've linked over here, we have a shrinking horizon MPC. And in the setting of a shrinking horizon MPC, so where we shrink our horizon, we can modify this robust safety constraint to retain some form of recursive feasibility, right? From a practical point of view, of course, you all know you could always insert slack variables, which would in some way or form degrade your safety guarantees, obviously. We also implemented this in Carla again. So here we simply wanted to validate our, wait, how much battery have I left? Okay, there's something left. I got. So for those of you, I can't charge my laptop because the charger here doesn't work. That's why I just wanted to check. So here we have it in Carla, and we kind of validated empirically our guarantees. Theoretically, we were guaranteed 99.83% coverage for one step ahead predictions, and we were slightly above that. And we were also guaranteed that we had at most 5 safety violations, and we experienced 1 in practice. We also made a comparison with a Gaussian process. So we trained a Gaussian process, and in this case, the GP undercovered, it only had 70%. And as you know, GPs, they rely on a prior, so maybe we didn't select it carefully, might be, but it just illustrates the benefit of kind of a frequentist methods like conformal prediction over a kind of more Bayesian method, I think. All right, so this is kind of good. One thing I would like to talk to you about is now distribution shift. So we're getting back to the question that we had in the beginning. Who of you has heard about distribution shifts? A few. Okay, so it's a very broad term that is being used in this domain that sometimes have people interpret it differently. I want to define it in the following way. For me, a distribution shift is when the design and the deployment conditions are different, right? I design my systems under certain conditions, and when I deploy it, those conditions have changed. Then I talk about a distribution shift. For instance, what we talked about before is we collected a data set of pedestrians, right? This could be close to a nursing home, old people, but now we want to deploy our system close to an elementary school with young children running around. Obviously, the walking pattern of these are different, and our safety guarantees wouldn't hold necessarily anymore, right? Another example is if we have data from a photorealistic simulator like NVIDIA Isaac Drive, looks really realistic, right? And then we have the real world. While it's close, arguably it's not the same. Okay. So technically, when we have distribution shifts, we don't have any safety guarantees anymore. There's some literature that shows that these conformal prediction guarantees degrade gracefully, meaning that if we have a small distribution shift, we only have small violations of the 1 minus delta bound, but generally it doesn't hold anymore. However, what we can do is there are versions to robustify these conformal prediction guarantees. One of those is robust conformal prediction, where we assume that the calibration data is drawn from some distribution R. Our test data is drawn from some distribution R0, and we make the assumption that these two distributions are epsilon close. And they're epsilon close in terms of a distance between distributions. Here, for instance, the F divergence, total variation, or KL divergence. There are other papers that have other type of statistical distances. I think one is Levi-Prokhorov, so there's a bunch of papers on that. Importantly, though, is if we know this holds, if there's a bounded distribution shift, then we can modify our conformal prediction argument. We again get the same guarantees that the test data point is bounded by some C tilde, but the C tilde here is now not a 1 minus delta quantile, but a 1 minus delta tilde of epsilon quantile, okay? So the delta tilde is a tightened quantile, so it's smaller than the delta we have selected, and it depends on epsilon. So the larger our distribution shift is, the more we need to tighten our quantile. The more conservative will inflate these prediction regions, so to speak, okay? Now, how do you compute this? Well, it's a solution of a set of convex optimization problems. It's basically described in here if you're curious. The important part here is that there are some trade-offs, right? First of all, since you're looking at a tightened quantile, you need more data. So you have increased data requirements, you need more calibration data, and you can quantify how much more you need. And you may not be able to select arbitrary delta, arbitrarily small delta. So there are these trade-offs. You have kind of bounds on the delta that you can pick to begin with and the amount of data that you really need. Okay, so this is something to be aware of. But then you can just go ahead. You can design controllers. You can design verification algorithms. And we'll see more of this later on when we talk about runtime verification. Okay, so what if the distribution shift is not bounded and is kind of too large, right? What can we do then? Well, there are adaptive versions, and this is relevant to the question on the Kalman filter that we had. Instead of using offline data, we can basically build our prediction regions from a stream of online data, okay? The way this works, very high level, is the following. We kind of compute our empirical coverage over the data that we have observed so far that may shift, right? So this E of t basically means, well, we assign 0 if our prediction region is correct and 1 otherwise, okay? And we compare this coverage, this empirical coverage, to what we're aiming for ideally, to our delta. We multiply this error that we're currently observing with a learning rate, and then we update our coverage level that we're using to compute our quantile. So this is an online type of algorithm. And we can, in the same way, compute prediction regions. We can design an MPC, but importantly now, we get different guarantees. Again, if this MPC using these adaptive regions is recursively feasible, we find an on average safe controller, meaning that we average pointwise, so in time, over our safety constraints. And we see that now this pointwise average only holds with 1 minus delta minus a correction term. And this correction term asymptotically, as capital T goes to infinity, goes to 0, okay? So you get on average safety and you get asymptotic type of guarantees. So this is important to be aware of. Yeah. Now, we implemented this on a case study where we had a drone that was avoiding a flying frisbee. The flying frisbee had nonlinear dynamics, had some noise on it. And I don't want to spend too much time on it. I just want to show a comparison. So our method, shown here in this column, compared to a method of my collaborator in an extended Kalman filter, we were aiming here for 97.5% coverage guarantees, right? Importantly, the methods that we compared against had 100% because they were overestimating the uncertainty that was really there. And we could see this by comparing, looking at the average distance of the drone to the frisbee, which was here 14.2 meters and here 5.27 meters, while our method was more realistic, estimated uncertainty more realistically with 2.91 meters and 99.2% coverage. Okay. And you can see the same thing here for a different kind of coverage level. So you can, in some way, deal with distribution shifts, either with robust versions of conformal prediction or with these kind of adaptive versions or combinations of those. You can do that too. And what we can also deal with is temporal logic specifications. I think most of you here at least have heard of temporal logic specifications. It's high-level specifications that go beyond the cases we looked at so far, which is going from A to B while avoiding obstacles, right? Now, you know about temporal logic. I usually have a slide to explain it to people that don't. So, you know, it's Boolean logic equipped with temporal operators. You can express high-level specs. Well, here, I just picked an example to illustrate it to people. Always avoid region E. Every hour inspect regions A and B. Whenever the battery level is low, recharge in C or D, right? And always between some time turn on communication. So these Boolean temporal objectives that you've probably seen a couple of times in licentiate or PhD defenses. The important part here is there's underlying syntax and semantics. And for each temporal logic formula, which we denote here by phi, we have a performance measure raw phi. And as you know, this performance measure is positive if we satisfy the specification, and it's negative if we violate it, okay? And the more positive it is, the better it is for us. So it's really a performance measure in some sense, right? Or in this community also referred to as a robustness measure. Now, what we're looking at is the following problem now. We have a temporal logic task with a performance measure that is defined over our robot or our system and the environment. So for instance, the pedestrians. And the way we proceed starts similarly to before. We make observations of the environment. We make predictions of the environment. We compute our prediction regions. But then we need to do something smarter because the specification is more complex. And what we're doing here is we're computing a robust performance measure raw bar of phi that is evaluated over our prediction. Specifically, we're computing the worst case performance that we can obtain over all the states in our prediction regions, okay? And then we're kind of we're optimizing over these. We're trying to maximize this worst case or this robust performance measure by picking control inputs correspondingly. What we can show is that we can solve this recursively on the structure of the logic specification. So we get a mixed integer linear program, okay? And we can compute this kind of efficiently in this MILP world, that kind of logic specifications can be solved in general. Okay? Omitting details here, just showing a small kind of case study where we have a leader-follower example. basically a leader that is going that is going to the blue regions in some time intervals, avoiding obstacles, and a follower that is kind of doing the same is going to this region. But the follower is supposed to follow the leader, which is the dynamic agent in this setting, with some distance. So this is kind of the coupled constraint with some probability. And as you can see here, this is really accomplished. In the paper, you can also find the statistical plots again. Okay, so this was the second part of the talk. Any questions on this at this point? All right. Then
I have a question.
yes.
So you point out two examples of like in the distribution shift, you train like a person walking and then go to like a school.
Yeah.
Have you worked on like interaction between the agent and?
It's a really good question. That's what we're currently working on. Yeah, because that's inducing a distribution shift, right? So far, there's a strict decomposition or for the lack of a better term, decomposition of the system dynamics and the dynamic environment, right? But ultimately they're coupled. There's your control action will affect how the environment will behave in some way or form. And what we're seeing is in the experiments that we've been running, at least, if the safety constraint is kind of, I don't want to say conservative, but isn't getting too close to the agent, there's limited interaction. The effect won't be large, right? If I don't threaten the pedestrian will not react in some way, right? But if I drive really close, the pedestrian may run away, and there may be an interaction. So the question is how to deal with this kind of more challenging problem, because the distribution of the pedestrian will change effectively. One thing that we've been looking into is to model the interaction using interactive models such as navigation functions or whatever is there, and to kind of propagate this through. Turns out this is kind of difficult to do. So there are other approaches. The adaptive approach kind of can deal with it. But it's weaker guarantees. So we're looking into some iterative approaches to solve this instead. But it's an open problem, actually, I would say. Yeah. There are a couple of papers, really, I think 4 or 5, that use adaptive CP. Pian also has one, who you know, on the adaptive CP to deal with this interaction. But generally, to get really strong guarantees like the ones in this clean setting that I presented is difficult to get. Yeah. So what I would do, I guess I would use like in practice, if I'm putting aside kind of I would like to get clean guarantees, then I would use a combination of adaptive conformal prediction and robust conformal prediction. We have some paper on that. So the adaptive one kind of adapts on it, and then I use trajectory data and I robustify it slightly against some distribution shift. So that's how I would deal with it. But yeah, that requires careful tuning on top, I would think. Any other questions or?
Hi, may I ask a question?
Of course.
Can you hear me?
Yes.
Yeah, thank you. So I have 2 questions. The first one is this, like the measurement of this distribution shift of the environment. So I was wondering if like this either K divergence or KL divergence you considered can cover those like partially observable environments. Say that there are some hidden variables that you're not considered. Can it cover that situation? Another, okay, maybe you can.
Can I answer to that first? Otherwise, I'll
Yeah, sure.
question. So here in the setting, we don't have hidden variables. We assume that we know the state. We've worked on state estimation as well. It gets more difficult though. So there may be a connection for partial observability and kind of the robust CP framework. I think it's an interesting idea. We haven't looked into it or thought about. Yeah.
Okay. Yeah, that sounds interesting to me as well. The other question, maybe it's just I didn't get it correctly, is that you mentioned that there's a variable I, or that indicates the mission steps you look into the future, and I was wondering how you actually choose this number in practice, because this mission step can be fixed in some simple environments, like you're at a crossing road, you have some time boundary. But what if it's like complex navigation goal that you don't know, like this horizon you want to look into?
We have picked one T, one mission horizon, and we haven't.
Yeah.
No, I mean it's a really valid question, right? Because we're operating in this finite domain. But I think if you go more towards asymptotic guarantees, right? We haven't talked about stability or any sorts of that, right? If you go more into infinite missions, long duration, there are a lot of open questions how you can design these controllers and statistical arguments to have validity. So I don't really have a good answer to your question, except for that in our experiments we selected one T. We tried to force the mission over that, and that kind of worked. Yeah, how this would look like more in an open world with variable mission horizons is, I think, something to think about.
Yeah, okay. Thank you.
Cool. All right. Any other questions on this? I mean, otherwise we can also chat a bit more offline. Let me get the next part. Oh, I should share. All right. So second part of the control synthesis. So more generally, we want to like we focused on a specific problem, right? Where we said, okay, we want to focus on uncertainty in the environment, right? It wasn't so much about uncertainty in the control system itself, right? We said we can model it accurately. So we want to focus on decision making and control now more broadly. So why would we be interested in solving decision problems under uncertainty? Well, to begin with, the system dynamics may be stochastic or affected in some way by non-determinism. For instance, we have a company, Brembo, it's an Italian company that we're working with. Gregorio is nodding, he knows them. They are interested in kind of modeling braking behavior at high performance. And I can't talk a bit or too much about details, but the issue there is when you're racing at high performance, it's really hard to model kind of accurately the dynamics. So there's a lot of non-determinism involved, right? Another reason could be that, and that's an obvious one, that you have sensor measurements. We just talked about partial observability, right? You may have sensors that may not capture all states or that may be corrupted by noise in some shape or form. We may, and we looked at this as well, we may have an environment that is uncertain and open-ended. And sometimes even control design itself is stochastic, right? I mean, if you look at some RL literature, the controllers are stochastic itself. So there are various reasons why you want to look at decision-making problems under uncertainty. The question is, how can we efficiently solve these decision-making problems which involve uncertainty? And there's a lot of existing work, but I want to set the stage first before I talk about that. So usually these are framed as chance constraint optimization problems, or CCO for short. The way you can think of it is you have a decision variable, as in any optimization problem here, X, that lives in Rn. You basically have a cost function, okay, that you want to minimize by selecting the right decision variable or an optimal one. And importantly, here you have a chance constraint, so a probability constraint defined over a constraint function f. And the constraint function f, as you can see here, is defined over the decision variable and a random vector y. And this random vector y very abstractly captures all the uncertainty that you have in your system that you don't know. Okay, so it could be any distribution of this random vector. And you have, as is often the case, inequality and equality constraints. They're not too important here for what we're looking at. The goal then is you want to find a decision variable x star, so solving this problem that minimizes the cost function while satisfying all these system constraints, including these chance constraints. Examples of CCO problems, you can find them in many domains. One is portfolio optimization in finance. There you want to kind of maximize your expected return of kind of the assets that you're investing into, subject to limiting the probability of losing money, kind of, right? And subject to, well, the amount of assets that you're placing in the market, okay? Now, I guess what's closer to us is, or what we've already seen is, computing these prediction regions is also a chance constraint optimization problem. Because if you think about it carefully, what we've been doing in the previous part is we minimize kind of the volume, for instance, of ellipsoids, right? So we kind of shape these ellipsoids subject to the constraint that our robot trajectory or our pedestrians were contained in these ellipsoids with 1 minus delta probability. Okay, so we kind of solved the chance constraint optimization problem before already. Or you could do robot motion planning. For instance, you may want to minimize energy consumption subject to limiting the probability of a collision subject to your system dynamics, right? And this, I guess, is closer to us a little. What is the challenge in solving these CCOs? Well, the challenge is that you have the chance constraint in there, right? So you have and basically the probability is an integral, right? And it may be high dimensional, may be really hard to solve in general. And you cannot solve these CCO problems exactly. So you cannot solve in closed form unless you make simplifying assumptions. For instance, you need to know the distribution of y to begin with. What's often assumed is it's Gaussian, for instance, right? And even if you know the distribution of y, you need to make assumptions on the function f, for instance, being linear, okay? Then if you have a linear problem, Gaussian noise, you can solve the problem. We kind of know that. Now, if you look at examples in the real world, you often don't know the distribution, right? Like just thinking back of the first part of this control talk, we don't know the distribution of how pedestrians walk over an intersection, right? We don't know the distribution of our noise on the systems or on our sensors. And what a fairly common approach is also in industry is you take samples of your noise, right? And you form an empirical distribution. And that's kind of what is done here in some existing work. You sample calibration data again, y1 to yk, to approximate the chance constraint in some shape or form. For instance, there are sample average approximation approaches where you take kind of the sample average of how often you satisfy your constraint over your samples, okay? Or there is scenario optimization. I mentioned this in the beginning already, where there are different variants, but this is the kind of the first one you will encounter. If you read this literature, it's also referred to sometimes as a robust version of it, because you enforce that all the safety constraint, not safety, the constraint function f here is enforced for all samples that you're having, okay? We started thinking about this as well, and we started asking ourselves, well, can we use conformal prediction to solve these CCO problems, right? Just can we do it? And like what algorithm do we get? And then also kind of how does this compare to these other sampling-based approaches? And there are some connections that we kind of discovered. I won't be able to talk into too much detail about it. And then with left terrace, we looked more into can we solve chance constraint optimal control problems as well. That's what I at least briefly want to tell you about. First thing is conformal predictive programming. That's how we called it. Here we assume that we have not only a calibration data set, but an optimization data set of samples y1 to yl, all right? And if these samples are IID and they're also independent of some x that we pick, okay, so let's fix one x for now, then we note that simply by applying conformal prediction, we can get guarantees of this form, right? We know that f evaluated at x and the test random vector is bounded by the 1 minus delta quantile over f evaluated at the samples that we have. So this is just applying CP. And that kind of motivated us to formulate this CPP formulation where we approximate the chance constraint by using the 1 minus delta quantile over our optimization data, okay? So we're just saying we take an optimization data set, we enforce that the 1 minus delta quantile is smaller than 0, we keep the inequality, equality constraints and the cost function, and we solve this, okay? Now, questions are, how do we solve this problem? And we solve it similar to before. We encode this quantile by a linear program, then we can use the KKT conditions, or we can reformulate the quantile also as a mixed integer linear program, right? So there are ways to solve this, and we talked about this before. The other interesting question is, what kind of guarantees do we get from here? Now, talking about the guarantees, we again have a calibration data set. We define a nonconformity score here now as taking the optimal solution of the CPP problem from the first slide. But now we evaluate it over the calibration data that we're having. And what we then know is, well, if we have the IID assumption again, that at test time, the optimal solution and the constraint is bounded by the 1 minus delta quantile over our calibration data. Now, it's important here to note that this quantile is a random variable, but it's centered around 0 in practice. So we expect that this is 0 or close to 0, and by that we approximately solve our chance constraint optimization problem. And some key properties, I'm going through this a little faster because I don't want to spend too much time on it. I just want to give you the gist of it. The advantage of the CPP, the conformal predictive programming, is that you don't need to make any assumptions on the CCO. So some existing literature assumes that this constraint function f, for instance, is convex. We don't have to assume that here, for instance. The potential drawback is that we need an additional data set. We need to split our overall data in optimization and calibration data. And then we get these kind of guarantees. And also the guarantees are obtained after computing X star. So in scenario optimization, if you have convex kind of F, you know your bounds already before you solve the optimization problem using structures of convex kind of problems. And here we only obtain the bound after solving for X star. However, the guarantees that we obtain are tight. Some existing work, they have bounds that depend on the dimension of the problem. So they kind of scale with the dimension of X, and we don't have this here. There's no such scaling. And importantly, this kind of CPP framework provides flexibility with other variants of CP. So you could, for instance, use robust versions of CP, adaptive versions, and so on. Remember, everything that we talked about CP, it's all based on computing some quantile, maybe with a tightened quantile over here, right? So you could extend this to account for distribution shifts and so on and so forth. Small example, we have a case study here. We have a robot with linear dynamics and the control input, some noise on the dynamics as well. And we want to find control inputs to reach some region with probability. So a fairly simple example over here. We just evaluated the cost function for two different encodings using this bi-level formulation and the KKT conditions, as well as the MILP kind of encoding, and they roughly give the same results. And then we also looked at the empirical coverage, which was around 90% over here. So I don't want to talk about this in detail. The important part here is, because that's a bridge to the next topic I want to talk about, is this controller is computed offline. It's an open loop sequence, right? And with Lefteris together, we started looking into, can we design reactive kind of and feedback controllers? So here, our goal was to design a feedback controller to minimize a cost function while satisfying state and input constraints with a probability no less than 1 minus delta, okay? And importantly here, we want a feedback controller, not an open loop sequence as we would obtain by just applying CPP. We want to design a feedback controller pi of x of t in this case. And if we write this down, we get the following optimal control problem. We want to minimize, let's say, overall goal is to find control inputs that are parameterized in this way that minimize some cost function, okay? Subject to, in this case, linear dynamics, stochastic linear dynamics, subject to the constraints that our state and input constraints are kind of in some sets with probability 1 minus delta, all right? Now, how do we solve this problem? Since we have linear dynamics, we can conveniently split the stochastic and the deterministic part of our linear dynamics into two subsystems that we then treat differently. So what we do is we define this error signal ET, which is, well, the error between our state and some new state that we're introducing, some deterministic state. And we are enforcing also a feedback controller that has the structure of G, this is a feedback gain we're supposed to design, times the error that we're here defining, plus some open loop controllers V of t. And if you look at this carefully, you see that by the choice of this error and this control input, you can do a decomposition of this system into a deterministic part that is linear, so A times Z of t plus B of V of t, feed forward control input, and a stochastic part, where here E of t plus 1 follows basically the A plus BG, the feedback term, times the error plus the noise. Okay, so we have a decoupling here of the deterministic and the stochastic part. Now, the important part is we will deal with them separately. Now we can design an open loop or a feed forward term V of t here, while we can design the gain of this feedback controller to minimize the effect of the error system. Okay, and that's what we did. We designed the feedback gain to control the stochastic error dynamics. So we're controlling kind of the error itself at each time step. And the feedback gain G of E of t that gives you the control signal here. And without going into detail, we know already that these are, again, these multi-step prediction regions that we computed before, right? So we can compute this CE and CU, these bounds, by using conformal prediction, and we can optimize over G to minimize these regions, right? And that's what we did. We kind of used the methodology that we kind of saw before already to find feedback gains G to minimize these bounds on the error of, on the norm of the error and the norm of G times the error. Okay. And then we went ahead and we still had to compute these feed forward terms for the deterministic system. And that's what we did kind of by this open loop problem where we minimize the cost function subject to our deterministic linear dynamics and subject to input and state constraints. And here, importantly, we need to tighten these input and state constraints by the size of the kind of statistical regions that we computed before. Okay. And that, if we can solve this problem, so we do constraint tightening here again, and by doing this constraint tightening, we are guaranteed to satisfy the chance constraint that we did before. Okay, so I know this was a little fast. This was only 2 slides, but I think the important part here is we can design feedback controllers for linear systems here by decomposing the stochastic system into a deterministic and a stochastic part of the system. And we minimize kind of the error that we're having by the choice of the feedback gain. And then we tighten the constraints here accordingly in the open loop problem. And we obtain a feedback controller. Okay, so feedback and feed forward term in there. And there are some case studies that we did. So single navigation case study. I think here the specification was to stay. We had I think double integrator Lefteris, right? Was it? Double integrator system, and here the velocity I think was pointing in this direction, and we're supposed to stay in this kind of circle. And you see some realizations leave it, right? We're having probabilistic enforcement of our constraints, and the majority of our system trajectory stays in the circle though, and eventually converges to the origin, right? Lefteris also extended this recently for CDC to multi-agent systems and to signal temporal logic specifications. And here we have multiple agents, and they're supposed to go to these regions in respective color, and along the way handshake with other agents, so to speak. And yeah, it also works here. Without going into detail, I just thought this is a nice animation to show. With that, I think we can take another break of 5 to 10 minutes. And if you have questions, just feel free to come the break. And after that, we'll continue more. Thanks. Okay, we're back on Zoom. All right, so we have roughly 25 minutes for the last part, and I can go over this briefly. We're going to talk about predictive runtime verification, and this is something that is not directly related to control. So we're talking more about formal verification now. What we want to do is, or what we're motivated by, is that we want to look at systems such as this F-16 aircraft or this car. This is, by the way, we learned a control barrier function here for the car, right? You can see it's not always working really well, the learn controller, but that kind of motivates it because we want, during runtime, we want to monitor the system if it's violating a safety specification. And we want to even do this in a predictive fashion. So we want to predict safety violations with high confidence. Okay, so we want to know, well, is the aircraft gonna stall or crash, right? Or is the car gonna go over the line or not? And then we want to, when we detect that, we can take action accordingly, right? But this is the kind of predictive monitoring part. To set up the problem, we model the system as, again, as a discrete time stochastic system. So here we have the state at time 0, state at time 1, that gives us a trajectory, and the trajectory is again drawn from this distribution calligraphic D. And the problem is the following. We are given observations of the states up until the current time, t. So we know x0 up until xt. And we want to compute the probability that a performance measure, rho phi, defined over this random trajectory is satisfied, so is non-negative. And I'm mentioning this is a performance measure more generally, right? It could be a reward from an RL kind of algorithm, or it could, for the temporal logic people here, it could be a temporal logic specification and the robust semantics associated with it, right? So it's fairly general, and we'll tailor it to temporal logics down the line. The challenges of this problem are the following. Well, first of all, how do we predict behavior of stochastic learning-enabled systems, right? How do we predict behaviors of these systems? It's a more practical problem, like what predictors are we using to accurately predict these? And again, we could go fully learned predictors, we could go physics-informed learning-enabled algorithms, or we could just use physics models, right? So it's fairly general in this sense. More interesting here than is if we're using some predictor, how can we use these to design efficient runtime monitors? And again, you want to do all of this online. You want a safety monitor online, so you need to be able to run it, right? And as we saw, conformal prediction is basically a sorting algorithm. So there's hope that we can do this efficiently online. And the last one, sorry, I skipped over that. How can we get statistical guarantees? And we'll do that similarly to before. So motivated here slightly differently, yet similar for using conformal prediction to solve this problem is that, well, in this case, the system dynamics are not necessarily easy to model, right? I mean, if we have a learned controller or we have a really complex autonomous systems for which we have a controller already, it's hard to, maybe you can write down the equations, but analyzing it is quite difficult. But what we have is we're living again in a data-rich world. So we have data that describes the behavior of the autonomous system, either in simulation or maybe even in reality. So we have access to some sort of testing data. And we again make use of learning-enabled predictors here, with a goal to combine it with conformal prediction and design efficient runtime monitors. Now, before I go into the details, I'll show you two algorithms. I want to give you the high-level overview again. We again assume that we have this offline trajectory data set of calibration data. Then during runtime, like I said before, we assume that we know the states of the system up until time t. We use some predictor to predict the future behavior of the system, here denoted by x hat of t plus 1, x hat of t plus 2. Then we compute this performance measure or the temporal logic robustness over x hat, which are our observations and the predictions that we've made. But since we're using predictions, the question is, well, how good is this predicted performance measure? And how good are our predictions that we've made in the first place? And that's again where conformal prediction comes in. We'll see two algorithms to compute or to obtain guarantees of the following form. We will know that this performance measure over the random trajectory is bounded by the predicted performance that we can compute during runtime, minus some calibration constant C, and this will hold with high probability. And then instead of looking at this, which we don't know at runtime, we can look at this as a lower bound for a safety monitor to alert us. Okay. Now here, like I said, we propose two lightweight predictive runtime verification algorithms with statistical guarantees, and I'll show you a set of case studies. Well, here we're back to temporal logics. I think we can skip this. We've seen this already. We just have to endure until the animation is kind of done, and then we'll move on to the next slide. But yeah, I mean, the important part here is we can have any performance measure or specifically temporal logics. Okay, so first algorithm is the accurate algorithm, and you will see why I call it accurate in a second. We consider, again, a trajectory predictor or a system model, whatever you want to call it, where we predict the system behavior, capital T time steps into the future. So we again have a mission horizon time. We look at finite time type of properties. We again here used an LSTM just because we had it running already. And for the accurate algorithm, we can define it directly by choosing a specific non-conformity score. So here we're choosing the predicted performance, you see the X hat over here, minus the performance that we know over our calibration data. Okay, so we evaluate this non-conformity score of predicted performance minus true performance. And then we simply apply conformal prediction, again computing the 1 minus delta quantile over these non-conformity scores. And we get right away that with probability no less than 1 minus delta for a test trajectory, the predicted performance that we can compute at the current time minus the true performance that we don't know yet is bounded by C. All that we do now is we rewrite this. So we rearrange these terms. We put this on the other side and C here on the other side, and we get exactly the probabilistic lower bound that we were asking for. Okay. And now we can use the right-hand side here as a sufficient condition to give a monitoring kind of result in terms of violating specification if we want to. It's accurate. Maybe I should spend some time on telling you why it's accurate, because you don't lose anything along the way. The non-conformity score is defined directly on the performance measure level, and this will be as opposed to the second monitor. But let's evaluate this first. We looked at Carla again. We looked at two different learning-enabled lane-keeping controllers. So the goal here is we want to design controllers that minimize the so-called cross-track error, so the distance of the car to the middle of the road. And we have two of these. One is imitation learning. So we basically use behavior cloning, just use some data. We clone the behavior of the expert, and that's our neural network that controls the system. And then we have our work on learn control barrier functions that you can see over here, where we use also demonstrations to kind of learn a CBF that approximates the behavior of the expert at the safety boundaries. Okay, they work kind of, as you can see here, but what we wanted to do is, well, we wanted to see, can we predict unsafe behavior in the first place, and maybe even can we use the uncertainty information that we get to find the safest controller, right? So what we were aiming for is this guarantee for both controllers. And we set a safety margin here, or a probability threshold of 95%. And we looked at two specifications for both controllers. The first one is overall safety. For those of you that can't read temporal logic, this means always in steady state. So here, after 10 seconds, the cross-track error should be below 2.25 meters. Okay. So we're looking at steady state. So we're forgetting the first 10 seconds of a run where the car is kind of adjusting. And then we're looking at, do we go outside of the lane? Histograms are plotted here of the non-conformity scores. Importantly, the kind of confidence, this calibration constant C for the imitation learning controller is much larger. So there's more uncertainty kind of involved. While here, the C for the CBF controller is quite low, so giving you much less uncertainty. We also, well, we did an empirical comparison here. We had 95% coverage also empirically, so this kind of checks out. We also looked at the more complex specification. Again, for those of you that can't read temporal logic, this means in steady state after 10 seconds, whenever the cross-track error is above 1.25 meters, then eventually, within 5 seconds, for the next 5 seconds, the cross-track error should be below this threshold of 1.25 meters. It's really a controller reactivity, right? Meaning that if it does something bad, it should eventually be back to good behavior. And yeah, the histograms are shown here. And you can see here, still the confidence is a little, this constant C is a little higher over here. Again, we did empirical evaluation. We approximately have our 95% over here. So we can do monitoring, statistically valid monitoring. And on top of that, we get a measure of uncertainty and trust during runtime by the C, by which we can select kind of which controller may actually, which ones we prefer. Okay, so this works. And I promised you 2 monitors, and the second one is motivated by the fact that this accurate monitor can identify failures of your system, but it cannot identify the cause of a violation, of a safety violation, right? It's just telling you, well, you're going to be unsafe, right? So in other words, if this kind of sufficient condition here, this lower bound is positive, it gives an alert, but it doesn't really tell you where and when the car is unsafe, right? Is it safe in the next second or in the next 5 seconds? And that may, of course, tell you how your controller, how you should react, right? Should you go and just push the brakes immediately, or can you do that a bit more gently, for instance, right? So what we want is, at the end of the day, is we want an interpretable runtime monitor. So, and by interpretability here, what we understand is we want to get these prediction regions that we looked at before that give us more information about, well, where and when, right? And in the temporal logic sense, it may tell you where and when a predicate may be violated. And good thing is we know how to compute these already, right? So we don't have to talk about this again. We know how we can compute these blue regions. What we're doing then is, having computed these regions, as elaborated on before, is we compute again this worst case performance measure, meaning we take the worst case performance measure over all the states in our prediction regions, okay? Now, for a second, if you just have a performance measure that is some function, some convex function, for instance, you can conveniently compute that, right? For temporal logic specifications, it's maybe more complex. We'll talk about this in a second. But assume that you can compute this. Since you're capturing all the states in your prediction regions, it follows directly that this worst case performance measure is a lower bound for the true performance that you don't know yet with a probability of 1 minus delta. Okay, it follows immediately. And again, if you have a convex kind of performance measure, you can compute that directly. For the temporal logic people here, you can compute this efficiently as well, as follows. What you're doing is for predicates, if your time that you're operating in, this tau, if you want to evaluate the predicate at time tau, before or during the time that you have already observed, you can simply compute your predicate function, right? You know the state already, so you can just do that. If the time you want to evaluate the predicate over is in the future, what you have to do is you have to take this infimum over all the states in your prediction region, and you have to compute the worst case kind of predicate that you're obtaining for this. And here we're back to, well, if you have a convex predicate, you can compute this efficiently, right? If you have a non-convex predicate, you can also do some tricks. If you have, for instance, Lipschitz continuous kind of predicate functions, you can get over approximations as well. And for the Boolean and temporal operators, they're defined in their standard ways using min and max operators, right? So then you don't get this exactly, but you may get an under approximation of it, right? Now we compared these two in a case study. So what I want to show you here is this kind of plot where you see on the x-axis 100 trajectories, test trajectories. And in gray, you see the ground truth performance that you observe after the fact, while in colors here, you see the predicted performance minus this kind of constant, right? The lower bound that we computed. And what you can see here, while the interpretable method is accurate, is interpretable, there's a huge gap between ground truth and predicted kind of performance, telling you that you're losing something along the way, at least in comparison to the accurate method, where you see the bound is much tighter compared to ground truth, okay? And that kind of confirmed what I already said. Well, one is conservative, one is accurate. One needs more data than the other. And then, but for this one, you have interpretability. So what I would say is in practice, you want to run both algorithms. You want to run the accurate one just to detect failures, right? And you run the second one to, if you have a failure, to detect, well, why are you failing, right? So I think they're complementary. You want to use both.
Now, in comparison to some of the work in the literature, I think both algorithms have the benefit that they don't need any retraining when the specification changes, okay? Because we're using trajectory predictor, when the specification, this performance measure changes, all you need to do is you need to recompute the nonconformity scores and compute the quantile again. But there's other work that kind of predicts the temporal logic robustness, for instance, right? So you have a predictor for a specific specification. If you change the specification, you need to retrain a new predictor. So it's quite tedious. And as we saw before already, it's easy to implement this conformal prediction argument. Very briefly about distribution shifts, we have some work there, and I told you already why we may have those and why they kind of violate our guarantees or may lead to a violation of our guarantees. And I told you a bit about the robust version of conformal prediction already, right? Meaning that if we have a bounded distribution shift, then in the nonconformity score, then we can apply conformal prediction with a tightened quantile. Okay. And that's what we applied in this kind of runtime monitoring setting. We assume here that our test trajectory has a distribution of calligraphic D0. Our calibration trajectories have a distribution of calligraphic D. So what we compute or obtain offline follows this distribution, calligraphic D, and what we observe online follows D0. And we assume that these are epsilon close and some F divergence. Now, importantly, if we apply a nonconformity score to these trajectories, it holds that also the distribution, the induced distribution of the nonconformity scores is also bounded by epsilon. And this follows simply, so here this distribution R0 is basically R of X real, nonconformity of X real, and R, calligraphic R here is the distribution of R of X1, R of Xk of the calibration data. And again, this kind of follows, it's also bounded by epsilon by the data processing inequality. So it's something that follows immediately. And it means that we can, in fact, apply robust conformal prediction if we know a bound on the distribution shift of our trajectories. So we again go ahead, we design an accurate method, we define the same nonconformity score as before, predicted minus true performance over calibration data. Now we apply robust conformal prediction. So we're taking this delta tilde of epsilon. So we're tightening the quantile by the amount of distribution shift that we have. And we get similar guarantees as before. We have a lower bound for our performance in terms of the predicted performance minus the robust CP kind of bound, right? And we can do a similar thing for the interpretable method. I've omitted this over here. Very briefly, we get some experiments on a Franka manipulator in simulation, I should say. We have a pick and place controller that's taken from NVIDIA Isaac Sim. We have a training distribution of initial conditions that is given like this. So we have uniform distributions of the manipulator of X and Y position. And then I forgot what the third state was. And then we have a test distribution that changes slightly. It's still uniform, but we kind of vary it. And as you know, like these RL controllers, they may be sensitive to initial conditions. So that's what we want to analyze here. So we want to analyze robustness against variations in initial condition. The system spec we're considering here is SDL. So here we want the pick and place controller to pick a box, and then the box should eventually reach a goal location in some closeness or some, what is this, zeta close, I think. Zeta 1 close, and then we want that the box eventually also reaches a human inspector with some closeness level. And when the box is close to a human inspector, the speed should be below a certain threshold for a handover potentially, right? And you can see some trajectories given over here. The human operator is here, the handover kind of happens here, and the final position is down there. And very briefly, what we aim for here is we aim for 80% confidence. You know, we select 400 time steps as our current time, some K calibration data. And what we computed is in the simulator was that the distribution shift when we change the initial conditions is 0.051. So this is something we determined beforehand. Then we plot the nonconformity scores again of our calibration data. And we do a comparison with this kind of vanilla conformal prediction where we don't robustify. And not surprisingly, what you see is the vanilla CP version that is not robustified gives you the blue line shown here, while the robustified version gives you a slightly more conservative bound here shown in green, right? So we're inflating our regions, or we're making them a little more conservative to account for the distribution shift. Now we plot our coverage, these conditional guarantees. And what we observe over here is in blue, you can see the kind of vanilla method, the baseline, where we don't robustify, and we see it's not achieving the 80% coverage that we were aiming for. While the robustified version in orange is kind of achieving 80% coverage as desired, because again, we're robustifying. Here again, similar plot to before, just for comparison, we have 200 trajectories over here. We plot ground truth in blue, and we plot the lower bounds from the robustified and the non-robustified version. And we kind of see, well, this kind of, the coverage is kind of reflected in here as well. So here again in green, you see we're more conservative, our bound, but we achieve 80% coverage. Before wrapping up, I want to talk about multi-agent systems as well. We had an extension of the monitors to multi-agent systems. Here, importantly, we're not using STL. We're using a multi-agent logic, a spatial temporal logic that is called STREL. So STREL has so-called reach and escape operators. If you're interested in details, check out the reference 2 over here. Again, it's a logic that reasons like STL over temporal properties, but here also over graph properties. So if there's a multi-agent system that has a graph, you can specify, you know, how the behavior over hops in the graph should be. And well, you can see a video over here for some drones. I think it started already. So let me repeat that. Yeah, that was the wrong button. I think I need to share on Zoom again. Yeah. So here you have a couple of drones, basically 4 drones. This is a drone simulator. And you can see the monitor, it turns on over now, and every time it's green, it's telling you you're satisfying your specification. You're not colliding with the boxes over here. The drones are not colliding, and you're on track to reach your goal. And it will turn red in a while, and that's when, yeah, you see that the predictions in dashed lines here are kind of overlapping with the boxes, and you have, yeah, safety violation. So here, for instance, is one of those instances. And yeah, that's kind of your monitoring signal. And that's, again, just to show you that these monitors are efficient, and they even extend to multi-agent systems and then even to spatial temporal logic kind of specifications. And with that, I think this was the last slide. And thanks all for joining. We made it in time. And if you have questions, you can ask now, or also afterwards, just come to me and we go with that. Any questions, or should we just?
I have questions.
Yeah.
Just quick one regarding the multi-agent case. So here, when I had a check like on the logic, like yes, they can define logic over graphs, but for example, like the program remains like similar to
Yes.
SPL, right? Like,
Yeah, that's why I didn't.
It's just like that you can high level define, okay, the graph needs to remain connected, but it doesn't provide like a tool to make the problem simple.
It's even simpler here. It's a centralized monitor.
Okay.
So it's just a multi-agent specification, a spatial temporal specification where you can also enforce graph properties.
But what I never really understood in that is that how they check, like for example, because to check a graph property like connectivity, you basically need to access the graph and check that the graph is connected. But this problem for big network could be like also very complicated because like a graph is a combinatorial like structure versus so. Yeah, and like you said, if you do this kind of monitoring locally, you still need some connectivity. You need the information of the agents. Okay. Yeah. So it's just a way to specify. So we have a paper that is under submission right now where you could, for instance, if you don't have the information of the other agents. So what we're doing here is true or false, right? Yes. But if you don't have the information, you could have a question mark. Okay. Right? So there are these 3 valued logics. Georges Fanikos has also worked on those that you can use, right? And then you either you give a false if you know you violate your specification, you give true if you know you satisfy it, and you give question mark, for instance, if you don't have all the information or you simply don't know yet for other reasons, right? Okay.
right? So it's three valued logics.
Yes.
Yeah.
And one other like very small question that I wanted to ask. So like here, when you compute like the robustness, for example, like that you need to check, like you need to monitor, like do you have a certain like step size? You have a certain step size to check the robustness, right? Like
Yeah.
as a method.
Yeah.
What impact did you find, or if you have an idea, what impact do you have like in how you choose, for example, this step size of sampling somehow the robustness, because you're passing from like a continuous time program of
It's fully defined in discrete time here. So
Yes,
we're not
yes.
considering.
But what do you use, like 1 second? You just say like, okay, 1 second, we still like.
I don't even know. We would have to
Yeah.
ask Nick who made the simulations.
Okay, yeah.
No, I really don't know. I think it's I don't have an answer. I would assume it's like
1 second.
no, I think it's more here because it's just the monitor, right? They are really efficient, so you can run.
Push this.
You can run push the sampling time. Yeah. So I mean the bottleneck here, in fact, if we talk about this predictive verification in terms of compute, is not computing the non-conformity score. Is not computing the quantile. It's more computing the robustness. The robustness computation is the bottleneck.
But because here, like it is the bottleneck because it's a lot of min-max operation, right?
So that's really the complexity here that you're and the non-conformity scores, you can compute them, the calibration data once at least offline, right? So it's only during test time you have to compute
something that is recursive.
Yeah. And there's some trade-off, but the accurate one is the fastest one in most of the times, because for the interpretable one, you have this worst case, this inf over computation as well. Yeah. But in general, I would, you could run it at higher frequencies. Yeah. Or you could run the system at like 50 hertz and the monitor at a different frequency, right? You don't need to monitor it every time step. I think that's in fact what's probably happening. I think I had a discussion with Nick about this, that we run the monitor at I think 10 hertz or something.
Okay.
I would have to check with him. Yeah.
Super. Thanks.
Cool. Other questions? Thanks
Hi.
a lot for joining. Oh, there's one on, yeah.
Yeah, I have a question. So have you explored the marginal gain of your approach regarding different controllers? I see that you have chosen two types of RL-based controller. I was thinking that like how effective this would be if it comes to like either model-based or data-driven, like RL-based, and like these different types of controller. Another thing is that if it's RL-based, like we can train a super large model that is accurate or less accurate, but then what would be the effectiveness of this conformal prediction approach? I ask this because I'm thinking that if there is any like correlation in between, then it might guide us in model selection in runtime if we have such a mechanism.
Yeah. I'm not sure if you can make a general statement about, I think what you can do is if you have a selection of controllers, you can select the controller that performs best with conformal prediction. You could maybe also use it to retrain a controller and to see why something fails, to use that information to augment your data set and retrain. These are kind of the connections I see, but yeah, that's I think where I would start with going around this, or how we have thought about it. Yeah, we've also tried to use conformal prediction to train RL controllers. It didn't work too well, so we instead came up with safety filters for RL controllers, conformal predictive safety filters. But yeah, directly more tightly integrating it, we haven't done it. Yeah.
Okay, thanks.
All right. Time for lunch, I guess. Thanks.